Hello, this talk will be on adaptive sketches for robust regression with important sampling by Sepid M. Mahabadi, David Woodruff, and I'm Samson So. So in the regression problem, we're given a matrix A that has dimension n by d, and we're also given a vector B that has dimension n by 1, and we want to find the vector x that has dimension d such that ax equals b. So here, A is a set of predictor variables. It's also known as a set of feature variables or design matrix. And B is the response variable, for example, measurements or dependent variables. So even though there may be a ground truth, often the data is imperfect and n can be much larger than d, so the system is overconstrained, meaning there may not exist a perfect x such that ax equals b. And therefore, instead of finding a vector x such that a equals b, it suffices to just find a vector x such that ax is approximately equal to b. Or perhaps that's the best thing we can do. So what does it mean to find a vector x such that ax is approximately b? Well, given a loss function L, we want to find a vector x that minimizes the loss ax minus b. And here we'll define the loss vector, or the loss function, ax minus b, as the sum of the components of the coordinates of the vector ax minus b. In particular, this means that we'll take the measure function applied to the first coordinate, which is the dot product of A1, the first row of A, with x, minus the first coordinate of B. We'll take the measure function of that, add that to the measure function applied to, let's say, the second row of A dot product of x, minus the second coordinate of B, and so forth. And here we're just given some arbitrary measure function m, but our choices of m could have different meanings depending on what we choose. For example, if we set mx to be x squared, then we get the least squares regression problem, or the L2 regression problem. Or if we set mx is equal to the absolute value of x, then we get the least absolute deviations problem, which is the L1 regression problem. And these have various trade-offs. For example, for the L2 regression problem, there's a unique solution, but the solution may be not as robust to noise as L1 regression, for example. On the other hand, there may not be a unique solution for L1 regression, but it may be more robust to slight modifications in the actual data that we receive. But ideally, the measure function m should be non-negative and monotonically increasing with the absolute value of x, and also smooth for some definition of smooth that perhaps you can imagine. So instead of computing instead of computing regression directly, because for some problems there may not be a closed form solution for regression, what can we do? Well, one thing we can do is we can take gradient descent, and so we can start with a guess x0 in the d-dimensional space, and we can run the gradient descent and compute the full gradient. And then for some learning rate eta, we can perform the update rule so that the current iterate, let's say xt, we add eta times the learning rate times the full gradient applied to the current iterate, and that gives us our new iterate x to the t plus 1. So this is a good convergence rate. Gradient descent is known to have a good convergence rate, but there could be poor computation time because computing the full gradient is expensive when n is large. We really have to look at every coordinate of this matrix A to compute this gradient, and we need to do this for each of the iterates that we run. So instead of writing gradient descent, we can instead start with our guess x0, and we can run stochastic gradient descent SGD by sampling a gradient and performing the update rule, where instead of multiplying the gradient by just the learning rate, now we also need to rescale by the inverse of the sampling probability pi sub t. And this is to get kind of like an unbiased estimate of the gradient. So here, we still have our same learning rate eta, but p sub I sub t is the sampling probability for the gradient. Now, SGD is also known to have good convergence rates. For example, t is equal to roughly 1 over epsilon squared times the variance squared. If we set that to be the number of iterations, then this suffices to achieve an epsilon approximate to the optimal value. And again, here, sigma is the variance of the sampling procedure, actually sigma squared, and mu is a parameter that's related to the learning rate. So how should we interpret the variance sigma? Well, if the gradient is uniformly sampled, then the sigma could be the variance could be very large. For example, consider the case where we have a matrix that's all zeros except for the very first row. Now, the first row is the only non-zero row, but it's only sampled with probability 1 over n if we do uniform sampling because there are n rows, and the first row is only one of these n rows. So the variance is n times the optimal variance because once we choose to sample the first row, whenever we do sample it, we need to rescale the first row by the sampling probability, which is 1 over n. So the first row gets rescaled by n. So yeah, the variance here is now n times the optimal variance, which occurs when we just choose to sample the first row deterministically so that we always output the first row. And in that case, the first row won't get rescaled. Okay, so the optimal variance occurs when we always sample the first row and output that as the gradient. But for uniform sampling, this only happens with probability 1 over n. So from this example, we can already see that perhaps a better strategy than uniform sampling might be to apply importance sampling, where we instead sample each gradient with probability proportional to its norm. All right, so this is known as importance sampling. In fact, it can be shown via the Cauchy-Schwarz inequality that these probabilities are actually the optimal sampling probabilities for SGD. Meaning that if we choose these sampling probabilities, then SGD will have the fastest convergence rate possible. All right. So quick note here, I'm not promising that this is the fastest approach for convex optimization. There could be some other accelerated methods that would do better than SGD. All I'm saying is that if we commit to doing SGD, then the sampling probabilities that we get via importance sampling is known to be the best possible results we can get in terms of convergence. So this actually does yield a chicken and egg problem. And the issue is that if we want to compute the gradient for each index, well, this is just as expensive as computing the full gradient, right? And this is the reason we want to avoid the gradient descent in the first place, because we didn't want to compute the full gradient. And now we're saying that, well, we might have this approach that has more iterations than gradient descent, but fewer iterations than uniform sampling for SGD. But computing each of the probabilities is just as expensive as computing the full gradient, so we might as well just run gradient descent. So this gives the chicken and egg problem where we want to compute the probabilities in order to run SGD with importance sampling, but doing so, is just as expensive computationally as just running gradient descent. So natural question is whether it's possible to simulate importance sampling for SGD without computing each of the sampling probabilities. In this work, we say, yes, actually, you can. Given a smooth measure function for some definition of smooth, there exists an algorithm that performs t steps of SGD with variance that's within a constant factor of the optimal sampling probability distribution. And here, the algorithm uses roughly nd squared plus td squared preprocessing time, and td squared polylog, tnd computation time, and space, meaning that the algorithm can still work in the string model where we see the rows of A one at a time. All right, and then our algorithm just needs to take a single pass over the rows of A. It computes the data structure, and then this data structure is able to permit t steps of SGD. So some context for these results. Well, because of importance sampling, we should expect the number of iterations t to be much smaller than n. In particular, maybe for uniform sampling, SGD might have a large number of iterates if the variance is large, but this shouldn't be the case for importance sampling. So our runtime is significantly better for a lot of interesting sets of data. And it's better than both running gradient descent and also better than computing the sampling probabilities for SGD with importance sampling. And of course, it's also better than just running SGD with uniform sampling. As I said before, it only requires a single pass over the data. And Crucially, we can use a smaller number of iterations than SGD with uniform sampling, as I mentioned before, for a certain sets of data. If all the rows of A are uniform, then we can't really do better than uniform sampling. But for the example that I said before, where perhaps a single row of A is non-zero, then we can get a much smaller number of iterations with our algorithm. Okay, so how does our algorithm work? Well, there are two main ingredients. And the first ingredient is a sampler. And it's a bit cumbersome, so bear with me. So given a matrix A that has dimension n by d, a measurement vector B that has dimension n, an active parameter epsilon, which is between 0 and 1, we say that a data structure is a sampler if on a query X, it outputs a vector V such that the index I in n is selected with probability proportional to importance sampling, up to a 1 plus epsilon multiplicative factor and a 1 over poly n additive factor. So the sampling distribution is almost the correct sampling distribution. So once it commits to an index I, then output a vector V such that V is pretty close to the gradient that needs to report, which is AI times the dot product of AI with X minus BI. So the difference between V and the vector that should output is roughly an epsilon times the 2 norm of the vector that should output. So all step 2 is saying is that V is pretty close to the gradient that it should output. And crucially for SGD, this vector V needs to be an unbiased estimate of the actual gradient. Okay, so we say a data structure is a sampler if it guarantees these 3 properties. And in fact, this data structure should permit adaptive sampling, meaning that the data structure should be built while it's processing A, but then the vector X, the query should be able to arrive after this data structure is built, and then the data structure can still output this vector V with the correct distribution. And it should extend to what we call smooth function G, so it doesn't just handle, this vector AI that I mentioned before, but it should handle generalization. So it should handle transformations applied to this vector AI. So we would like to use this G sampler as an oracle for importance sampling for SGD, because it outputs a vector. It outputs almost the right gradient with almost the right probability distribution. So this seems great. In fact, we would like to iteratively call this data structure on SGD iterates to sample gradients from the importance sampling distribution. And it seems like we can do this, right? Like if we want to run T steps of SGD, then maybe we can just build T of these data structures, apply it T times to get T gradients, call it a day, and run SGD. But this actually doesn't work because subsequent iterates are not independent of the randoms in the data structure. So if we just build one data structure and run it T times, the issue is by the time we apply it to the third iterate, well, the value of the third iterate depends on the output of this data structure in the first 2 times. And so the value of the third iterate is not independent of the randomness in the previous steps. So we can't just build one data structure and query it T times and use that for T steps of the SGD. That won't work because, well, it's not clear if it works, but at least the analysis says that doesn't seem to apply that works because there's not independence between the randomness and the data structures. Okay, so one possible fix is what I alluded to before. Maybe we can, instead of creating one sampler for T steps, maybe we can just create T separate samplers, one for each SGD iteration. But in fact, this also doesn't work because each sampler will use a separate pass over the data. So even though we can all build the T structures in one single pass of the data, the runtime, the pre-processing time will still be essentially T and D, which is prohibitive. It's still too large, right? We want to avoid runtime T and D because that's the time that would take to do gradient descent. Okay, so we can't build T separate samplers and use each sampler for a separate SGD iteration. That takes too long. So the question is, how do we avoid runtime T and D, given that we have this first ingredient that just outputs, an approximately correct gradient with approximately the right distribution? Well, our second ingredient is a data structure that what we that handles what we call bucketing for SGD. So first, we remark that the leverage scores of the rows of A correspond to the maximum probability that the row can be sampled. So the sampling probabilities for the rows of A will differ depending on the current iterate for SGD, but they're going to be upper bounded by the leverage scores of the rows of A. So if we remove all the rows of A with leverage score more than 1 over t, and store them explicitly, then the remaining rows that haven't been stored explicitly can only be sampled with probably less than 1 over t. So the point is that if we partition the remaining rows of A into t separate buckets, and then we create log n t samplers for each bucket, then none of these buckets should be hit more than log n times, and so we should have enough samplers for each of these buckets. And the crucial observation here, again, is that none of these samplers should be hit more than log n times, because the rows in each of these buckets will all be sampled with very small probability. So this is a computation that we do, but once we do so, the overall framework is that we separate the rows of A into the heavy rows and the light rows. The heavy rows we store explicitly. The light rows we create G samplers for. And now for each of the SGD steps, first we decide whether we sample a heavy row or a light row. If we sample a heavy row, we have them explicitly. If we have a light row, we have a separate G sampler for each iteration that we hit one of these T buckets. And that's it. That's our whole algorithm. So in summary, given a smooth measure function, we show that there exists an algorithm that performs T steps of SGD with variance that's within a constant factor of the optimal sampling distribution. The algorithm uses roughly ND squared plus TD squared preprocessing time and roughly TD squared computation time in space if it's in the streaming model. And actually, our approach also translates to importance sampling for second order optimization, for example, importance sampling for Hessians. And it can also handle higher degree polynomials for measure functions. So I'm actually hiding a lot of details. There are some technical details for the actual sampler, but I just want to give an overview of the main results in our paper, and hopefully this whets your appetite a little. And if it does, I'd highly encourage you to check out the finer details in the paper. Thanks.